Welcome to the lecture on transmission lines and RF system. I am Dr. K. Padmapriya, Assistant Professor, EC Department, Government College of Engineering, Bodinaikanur. Let's see about Unit 1, Transmission Line Theory. We have two modules in it. Let's watch the first module in Unit 1. General theory of transmission lines. A transmission line is a device designed to guide the electrical energy from one point to another. It is used to transfer the output RF energy of a transmitter to an antenna. This energy will not travel through normal electrical wire without great losses. Although the antenna can be connected directly to the transmitter, the antenna is usually located some distance away from the transmitter. On board ship, the transmitter is located inside a radio room, whereas the antenna will be mounted on a mast or a post. A transmission line is used to connect the transmitter and the antenna, and it has a single purpose for both the transmitter and the antenna. And its only purpose is to transfer the energy output of the transmitter to the antenna with least possible power loss. So how well this is done will depend on the special physical and electrical characteristics like impedance and resistance of the transmission line. Transmission line theory. The electrical characteristics of a two-wire transmission line depends primarily on the construction of the line. The two-wire line acts like a long capacitor. The change of its capacitive reactance is noticeably as the frequency applied to it is changed. Since the long conductors have a magnetic field about them when electrical energy is being passed through them, they also exhibit the properties of inductance. The values of inductance and capacitance presented depend on the various physical factors. The types of line used, the dielectric in the line, and the length of the line must be considered. The effects of the inductive and capacitive reactance of the line depend on the frequency applied. Since no dielectric is perfect, electrons manage to move from one conductor to the other through the dielectric. Each type of two-wire transmission line also has a conductance value. This conductance value represents the value of current flow that may be expected through the insulation. If the line is uniform, then one small section of the line may represent the several feet. A transmission line has the properties of inductance, capacitance, and resistance, just as the more conventional circuits have. Usually, however, the constants in conventional circuits are lumped into a single device or component. A coil of wire has the property of inductance. When a certain amount of inductance is needed in a circuit, a coil of the proper dimension is inserted. The inductance of the circuit is lumped into one component. Two metal plates separated by a small space can be used to supply the required capacitance for the circuit. In such a case, most of the capacitance of the circuit is lumped into this one component. Similarly, a fixed resistor can be used to supply a certain value of circuit resistance as a lumped sum. So, ideally, a transmission line would also have its constants of inductance, capacitance, and resistance lumped together. But unfortunately, it is not the possible case. Distributed constants. Transmission line constants called the distributed constants are spread along the entire length of the transmission line and cannot be distinguished separately. The amount of inductance, capacitance, and resistance depends on the length of the line, the size of the conducting wires, the spacing between the wires, and the dielectric between the wires. The electrical lines used to transmit the electrical waves along them are represented as transmission lines, and the parameters of the transmission lines are resistance. R is the loop resistance per unit length of wire, ohms per kilometer. Inductance L, which will have the units Henry kilometer, the loop inductance per unit length of the wire, and the capacitance C is the loop capacitance per unit length of the wire, represented in farads per kilometer. and conductance G is defined as the loop conductance per unit length of wire moves per kilometer. Hence, the transmission line is also called as distributed network. So, some of the applications of transmission lines are, they are used to transmit signal, that is the electromagnetic waves, from one point to another. It can be used for impedance matching purpose. Also can be used as circuit elements like inductors, capacitors. They can be used as stubs by properly adjusting their lengths. Wavelength of a line is the distance the wave travels along the line while the phase angle is changing through 2 pi radians is a wavelength. Characteristic impedance is the impedance measured at the sending end of line, and it's given by Z0, which is equal to Z by Y. Z equals R plus J omega L is the series impedance, and Y equals G plus J omega C is the shunt admittance. Secondary constants of a line are characteristic impedance, propagation constant. Since the line constants R, L, C and G are distributed through the entire length of the line, they are called the distributed elements, and they are also called the primary constants. The transmission line, it is an infinite line. An infinite line has to be considered. So, the infinite line will have a finite length on the line. So, a finite line will have a finite length on the line. It is a line which is terminated in its characteristic impedance. So, ZR will be equal to Z0, so that the input impedance of the finite line is equal to the characteristic impedance, that is S equals Z0. So, an infinite line is a line in which the length of the transmission line is infinite. A finite line which is terminated in characteristic impedance is also terminated as an infinite line. So, for infinite line, the input impedance must be equal to characteristic impedance. So, consider the symmetrical T network shown here with two impedances, that is Z1 by 2 and Z2, and the characteristic impedance is Z0 and the input impedance is Zn. So, the value of Z0, that is the image impedance for a symmetric network, can be easily determined. So, in this figure shown, it is terminated in its image impedance Z0, and if Z1 and Z2 is equal to Zt, we assume this condition and we go on for the solutions for it. So, it is used to find the voltage and current at any points on the transmission line, but the transmission lines behave very oddly at high frequencies. In traditional circuit theory, the wires connect devices but have zero resistance. There is no phase delay across the wires, and a short circuited line always yields zero resistance. For high frequency transmission lines, things behave quite differently. For instance, short circuits can have an infinite impedance. Open circuits can behave like short circuited wires. The impedance of some load ZL is equal to XL plus JYL can be transformed at the terminals of the transmission line into an impedance much different than ZL. For example, a sinusoidal voltage source with associated impedance ZS is attached to the load ZL. The load and the source are connected via a transmission line of length capital L. Since the antennas are often high frequency devices, the transmission line effects are very often important. If the length L of the transmission line significantly alters Zn, then the current into the antenna from the source will be very small. Consequently, we will not be delivering power properly to the antenna. The same problem holds true in the receiving mode. A transmission line can skew impedance of the receiver sufficiently that almost no power is transferred from the antenna. A great antenna can be hooked up to a great receiver, but if it is done with the length of a transmission line at higher frequencies, the system will not work properly. The examples of common transmission lines include the coaxial cable, the microstrip line, which commonly feeds the patch antenna or a microstrip antenna, and the two-wire line, it's shown below, the coaxial cable, microstrip line and two-wire line. So, to understand the transmission lines, we will set up an equivalent circuit to model and analyze them. So to start that, we take a transmission line of length L and divide it into small segments where each small segment will have a length of dz. Then we will model each small segment with the small series resistance R dash and series inductance L dash and shunt conductance G dash and shunt capacitance Z dash with for a small length dz. All the transmission lines will be represented as the above diagram, whereas in case of the microstrip transmission lines, the parameters will be different. That is, your R dash will be the DC resistance of 1 meter of transmission line. G dash will be the isolation between the two conductors of the transmission line. C dash represents the capacitance between the two conductors that make up the transmission line. L dash represents the inductance for 1 meter of the transmit line. These parameters can be derived for each transmission line. So, general solutions for the voltage and current. A circuit with a distributed parameter requires a method of analysis somewhat different from that employed in the circuits of lumped constants. Since a voltage drop occurs each series increment of line, the voltage applied to each increment of shunt admittance is a variable, and thus the shunted current is a variable along the line. Hence, the line current around the loop is not a constant as is assumed in lumped constant circuits, but varies from point to point along the line. Differential circuit equations that describes that action will be written for steady state, for which the general circuit equation will be defined with the components R, L, G and C. The omega L will be the series resistance in ohms per unit length of line, where Z equals R plus J omega L, and series susceptance mhos per unit length of line, where Y equals G plus J omega C. S will be the distance to the point of observation measured from the receiving end of the line. I is the current at any point in the line, and E is the voltage between any conductors at any point. Between the conductors at any point, and L is the length of the line. The below figure, it shows that it's made of infinite multi sections. So here the incremental section of length ds, and it carries a current I. The series line impedance being Z ohms, and the voltage drop in the length ds is dE equals I Z ds, where rearranging this equation 1 will give you dE by ds equals I into Z. The shunt admittance per unit length of line is Y mhos, so that the admittance of the line is Y ds mhos. The current Di that flows across the line or from one conductor to the other is Di equals Ey ds, which is their equation 3, and by rearranging the equation 3 we get Di by ds equals Ey. So the equation 2 and 4 may be differentiated with respect to S. So we get d square E by ds square equals Z into di by ds, whereas d square I by dz square equals Y into d by dz. While substituting the values there, we get d square E by ds square equals ZYE, and d square I by ds square equals ZYI, which is your equation 5 and 6. And this differential equations of the transmission line, the fundamental to circuits of distributed constants, can be found from the final equation of E and I, where A, B, C, D are the arbitrary constants of integration. So, since the distance is measured from the receiving end of the line, it is possible to assign the conditions such that at S equals 0, I equals IR and E equals ER. Therefore, the equation 7 and 8 becomes ER equals A plus B and IR equals C plus D. So, this becomes the set of equations 9. So, a second set of boundary condition is not available, but the same set may be used over again if a new set of equations are formed by differentiation of equations 7 and 8. Thus, your final equation for IR equals A into square root of Y by Z minus B into square root of Y by Z. where ER equals C into square root of Z by Y minus D into square root of Z minus Y. So simultaneous solution of equation 9, 12 and 13 along with the fact that ER equals IR into ZR and that ZY can be identified as the Z naught of the line. That is, your Z naught is the characteristic impedance in which it is terminated, which leads to the solution for the constants of the above equation like this. So these are the set of equations for A, B, C and D in terms of IR and ER. And this remains the solution of the differential equation of the transmission line and is determined by the E and I equations 14. The above equations are useful for the voltage and current at any point of the transmission line. So after simplifying the above equations, we can get the final and very useful form of equations for voltage and current on K line and our solutions to the wave equation 2. So E equals ER cos h square root of Z into Y into S plus IR Z naught sin h square root of ZY S. I equals IR cos h square root of ZYS plus Z ER by Z sin h square root of ZY into S. This result indicates two solutions, one for the plus sign and other for the minus sign before the radical. Wavelength and velocity of propagation. The wave propagation is any of the ways in which the waves travel with respect to the direction of the oscillation relative to the propagation direction. We can distinguish between the longitudinal wave and transverse waves. For electromagnetic waves, the propagation may occur in a vacuum as well as in a material medium. Other wave types cannot propagate through a vacuum and need a transmission medium to exist. So the distance the wave travels along the line while the phase angle is changed through 2 pi radians is called wavelength. So lambda is equal to 2 pi by beta. The change of 2 pi in phase angle represents one cycle in time and occurs at a distance of one wavelength. Lambda equals V by F. So lambda, by rearranging it, the velocity V is equal to F into lambda, which implies V equals omega by beta, that is 2 pi F. So this is the velocity of propagation along the line based on the observation of the change in the phase angle along the line. So it's measured in miles per second if beta is in radians per meter. You know that Z equals R plus J omega L and Y equals G plus J omega C. Then gamma equals alpha plus J beta, which is equal to square root of ZY, which is again equal to RG square root of RG minus omega square LC plus J omega LG plus CR. So squaring on both sides we get this equation and equating the real parts and imaginary parts. So we get alpha and then by equating the imaginary part we get the equation for beta 2. So in a perfect line R will be equal to 0 and G will be equal to 0. So from the above equation it will be beta equals square root of equals omega into square root of LC. And the velocity of propagation for such an ideal line is given by V equals omega by beta. So it is the line parameter values which fix the velocity of propagation. Waveform distortion. The signals transmitted over lines are normally complex and it consists of many frequency components. So for ideal transmission, the waveform at the line receiving and end must be the same as that the waveform of the original input signal. The conditions require that all the frequencies have the same attenuation and the same delay caused by a finite phase velocity or velocity of propagation. When these conditions are not satisfied, then distortion will persist in the line. The distortions occurring in the transmission line are called waveform distortion or line distortion. It's of two types and it's frequency distortion and phase or delay distortion. In frequency distortion, the attenuation function will be a function of frequency. So it specifies the attenuation or loss incurred in the line while the signal is propagating. So when a signal having many frequency components are transmitted along the line, all the frequencies will not have equal attenuation. Hence, the received end waveform will not be identical with the input waveform at the sending end. And because each frequency is having different attenuation, such type of attenuation or distortion is called frequency distortion. Here, when the attenuation constant is not a function of frequency, frequency distortion doesn't exist on the transmission line. In order to reduce the frequency distortion occurring in the line, the attenuation constant should be made independent of frequency by using equalizers at the line terminals, which will minimize the frequency distortion. So, equalizers are networks whose frequency and phase characteristics are adjusted to be inverse to those of the lines, which result in a uniform frequency response over the desired frequency band, and hence the attenuation is equal for all the frequencies. Delay distortion. When a signal having many frequency components are transmitted along the line, all the frequencies will not have the same type of transmission. Some frequencies being delayed more than others, so that the received end waveform will not be identical with the input waveform. And some frequency components will be delayed more than the other frequencies. So this distortion is called phase or delay distortion. It is the type of distortion in which the time required to transmit the various frequency components over the line and consequently the delay is not a constant. So when velocity is independent of frequency, delay distortion does not exist on the lines. In general, the phase function is a function of frequency. Since V equals omega by beta, it will be independent of frequency only when beta is equal to constant multiplied by omega. In order to reduce the frequency distortion occurring in the line, the phase constant should be made dependent of frequency. The velocity of propagation is independent of frequency by using the equalizers at line terminals, which minimize the frequency distortion. Therefore, we conclude that a transmission line will have neither delay nor frequency distortion only if alpha is independent of frequency and beta should be a function of frequency. So this is the values of attenuation constant alpha and has been given in the equation. So generally alpha will be a function of frequency. All the frequencies transmitted will not be attenuated equally. So a complex supplied voltage such as voice voltage containing many frequencies will not have all frequencies transmitted with equal attenuation, and the received wave will be identical with the input waveform at the sending end. This variation ICDS is known as the frequency distortion. And for the phase distortion, the component beta is considered, and again the same way the delay between the transmitted and the received waves will give some distortion in it. So it is apparent that omega and beta do not both involve frequency in the same manner, and that the velocity of propagation will be general for some frequency. Frequency distortion is reduced in the transmission of high quality radio broadcast programs over wireline by use of equalizers at line terminals. These circuits are networks whose frequency and phase characteristics are adjusted to be inverse to those of the lines, resulting in an overall uniform frequency response over the desired frequency band. Delay distortion is relatively minor importance to voice and music transmission because of the characteristics of the ear. It can be very serious in circuits intended for picture transmission, and application of the coaxial cable have been made to overcome the difficulty. In such cables, the internal inductance is low at high frequencies because of the skin effect. The resistance is small because of the large conductors, and the capacitance and leakance are small because of the use of air dielectric with the minimum spaces. So velocity of propagation is raised and made more nearly equal for all frequencies. So that's all in the module 1 for unit 1. Thank you.